So in this class, we will discuss about the strain displacement relationships in polar coordinates. So we have learned in Cartesian coordinates about the strain displacement relationships. If u, v, w, if they are the displacements along x, y, z directions respectively, then epsilon x, epsilon y, epsilon z, they are the strains, normal strains. And gamma xy, gamma yz and gamma zx, they are the shear strains. And we learned about the relationship between them. Now similarly, you can always have the stress strain that is strain displacement relationships in polar coordinates. So in polar coordinates means in terms of r and theta. A point is represented by r theta. One is linear dimension, another is angular dimension. So in this case, let us define the stresses as sigma r, sigma theta and rho r theta. Corresponding the radial stress, the stress developed in the radial direction is sigma r. The stress developed in the circumferential direction, that is the circumferential stress or the hoop stress, that is sigma theta, and rho r theta is the shear stress. So this is the diagram which shows the stresses and also the strains and displacements in r and theta directions. So to understand about the polar coordinates, we have to consider a curved element like this at a distance, radial distance of r from the origin, and if you consider the thickness of the element as dr, so this arc length will be r into d theta, where d theta is this included angle, and the area of this elemental strip will be dA, that is r into d theta into dr. It is considered as a rectangular element. So length into width, that is r into d theta into dr, gives the value of this elemental area dA. Now the directions of the stresses will be along the radial direction. So sigma r is the stress. Of course, at both the edges it will be there. I have shown here tensile stress away from the element. And along the circumferential direction is sigma theta. Corresponding strains will be epsilon r and epsilon theta. Corresponding displacements in those two directions are u and v. So u is the displacement in r direction, v is the displacement in theta direction, and rho r theta, as you know, it will act along the edge in the parallel to the area. So shear stress rho r theta, if I take like this, the other one on the other side, it will be in the opposite direction, and here it will be like this and it will be like this, because you know that shear stresses act in the complementary manner. So this is the diagram which shows all the three stresses, sigma, sigma theta and rho r theta, and three strains, epsilon r, epsilon theta and gamma r theta, of course in a polar coordinate system. Now the strains are of course radial strain, epsilon r, epsilon theta is the circumferential strain, gamma r theta is the shear strain. Corresponding to the stresses, these are the strains. Now you can always have a relationship between these stresses and strains similar to Cartesian coordinate system. So if you want the shear strain, if you want the normal strain in r direction, that is epsilon r, it is given by 1 by e into sigma r minus mu times sigma theta. This is nothing but your generalized Hooke's law. So this generalized Hooke's law we have learned for Cartesian coordinates also in three-dimensional system. Similarly, epsilon theta is the normal strain in theta direction, which is given by 1 by e into sigma theta minus mu times sigma r, and gamma r theta is rho r theta divided by g. So this will give the stress strain relations, where E is the Young's modulus, G is the rigidity modulus, and mu is the Poisson's ratio. They are the elastic constants. So we are using the same set of generalized Hooke's law equations to represent the stress strain relations in polar coordinates also. Now another set of equations which give the relationship between strain and displacement. This is very important, since here this u is a function, u and v, they are functions of r and theta. Just like u and v, they are functions of x and y in the case of Cartesian coordinates. Here in polar coordinates, this displacement, they are functions of r and theta, where r theta represents the coordinates of a point. So the radial strain epsilon r is given by dou u by dou r. So you have to remember these relationships, because to solve problems, we are going to use these expressions directly. So epsilon r is given by dou u by dou r. Epsilon theta, which is the circumferential or the hoop strain, u by r plus 1 by r into dou v by dou theta. Gamma r theta, which is the shear strain, which is given by dou v by dou r plus 1 by r into dou u by dou theta minus v by r. So these are the expressions for the strain displacement relationships. Now let us try to solve a problem on the strain displacement relations. So in the given problem, u and v, they are given as functions of r and theta. So u is given as 5r square minus into sin 2 theta minus r theta cube. V is given as 10r cube cos 2 theta minus r square theta square. The question is determine the radial, circumferential and shear strains at the point minus 5 and pi by 3. That is r at r is equal to minus 5 and theta is equal to pi by 3, that is 60 degrees. What are the values of these strains? So strains means we have to find out epsilon r, epsilon theta and gamma r theta. So these three things we have to find out. Now let us go to the solution. So we have to use these formulae or expressions to find the strains. Since u and v are known as functions of r and theta, only thing is we have to differentiate them partially with respect to r and with respect to theta and substitute in these expressions to get the strain components. So let us find out epsilon r first. Epsilon r is the normal strain component in radial direction, dou u by dou r. That means we have to differentiate this with respect to r partially, treating theta as constant. You have to remember, when you are differentiating with respect to r, theta is taken as constant. When you are differentiating with respect to theta, r is taken as constant. Now let us find out dou u by dou r. So if you differentiate with respect to this with respect to r, 10r into sin 2 theta minus theta cube. So that is the expression you are going to get, because theta is taken as constant. Now at the point minus 5 comma pi by 3, at r is equal to minus 5, theta is equal to pi by 3, substitute the values, corresponding values for r as minus 5, theta as pi by 3, and if you simplify, you are going to get the answer as minus 44.45. So strain has no units, therefore it is just a number. Now here, one thing, in your calculator, when you are using this 2 pi by 3, if your calculator is in the degree mode, degree mode, then instead of 2 pi by 3, you have to put as 120 degree. In terms of degree, you have to substitute this. Of course, this is in radians. Theta will be in radians, so pi by 3 is okay. But when that theta is associated with some ratio, sin or cos, something like that, when the calculator is in the degree mode, you have to substitute that value in degrees. Please note that 2 pi by 3 is 120 degrees, because pi is 180 degree, pi radian is 180 degree, so 2 pi by 3 is 120 degrees. So this you have to take it as 120 degree in the calculator when you are using the calculator in degree mode. Otherwise, if you just substitute sin 2 pi by 3, you will get a different answer. Be careful about that. Similarly, epsilon theta, it is the normal strain in theta direction, like this, that is in the circumferential direction. Formula is u by r plus 1 by r into dv by d theta. So u by r, so already u is there here, divided by r means it is 5r into sin 2 theta minus theta cube. Okay, that's what you are going to get. And here plus 1 by r into dou v by dou theta. This you have to differentiate with respect to theta. Okay, with respect to theta, and then divided by r, you are going to get this expression. So all this you have to practice. Then finally you substitute the values of r as minus 5 and theta as once again 2 pi by 3. Pi by 3 you have to substitute. Once again here sin 2 pi by 3 means sin 120 degree, and this pi by 3 you have to substitute as it is and you have to calculate. So if you do that, you will be getting minus 445.34. Once again that doesn't have no units. Lastly, shear strain gamma r theta, the formula is dou v by dou r plus 1 by r into dou u by dou theta minus v by r. So this also v with respect to, we have to differentiate v with respect to r partially taking theta constant, dou u by dou theta we have to differentiate u with respect to theta partially creating r constant, and then we have to substitute all this and simplify. Finally you substitute for r for in the last expression r is equal to minus 5 and theta is equal to pi by 3, and once again here cos 2 pi by 3 term we have to take 2 pi by 3 as 120 degrees. So here it is degrees, but here it is in radian. So this is also 120 and this is also 120. So like that we have to take, whenever the angle is with some ratio we have to take the angle in degrees. Otherwise if it is not in ratio, if it is only theta, then you have to put it in radians only. This pi by 3 is in radian, 2 pi by 3 you have to take in degrees, and if you simplify you will get minus 672.6. So that also doesn't have any units. So finally at the point minus 5 comma pi by 3, these are the strain components or the given displacement field. So this is a simple example. So why I took this example is this is similar to your Cartesian coordinate system where x and y will be there. So there the formula is epsilon x is dou u by dou x, epsilon y is dou v by dou y, gamma xy is dou u by dou y plus dou v by dou x, like that. But here the formulas are different, so you should be careful when you are using polar coordinate system, because one is linear, another one is angular, so it will not be symmetric. You should be careful using the expression. So this example tells how we can calculate the strains given the displacement field in polar coordinate system.